So test 4, 25 multiple choice questions. Study guide this weekend, and it's just 25 multiple choice questions. We have quiz 4. That's going to be due November 24th. Okay, last day of class, the same day as the text, same day as your exam. The test is not cumulative. It's going to cover chapter 7 through 10. 7, 8, and then I bunched up 9 and 10. Hopefully you're watching the old videos, that lecture recordings, or just taking notes. So it's really going to be on your notes. We have a lab notebook that's due. I think I made it due November 20th, but you can check Canvas for that. Lab reports. So we're done with the lab. The only thing I need you guys to do is turn in your lab notebook and make sure you have all your lab reports turned in, molecular models, solubility within a family. If you're still doing this, to help you, we have those online drills, so do those drills. And then I have an extra credit Lewis structure assignment where you'll draw 40 Lewis structures. And then that due date is also on Canvas. I believe it's November 21st or November 20th. So it's 40 Lewis structures, and it's an honor system. You do these practice structures, 40 of them. Check your answers with my answers, and I'll give you 25 points towards your homework grade. All right. So I think that is where we're at. Tomorrow, or next week, is our last week together. So I plan, okay, that's the plan, to do a Monday, Wednesday, Friday, and then next week should be all review. So do come with your questions for next week. All right. And I'll also post a study guide for the exam. I'm still working on the guide, and that should be available this weekend as well. All right, so let's continue our discussion on Lewis structures. Let's just throw in some examples. Okay, so practice is really what makes perfect in terms of building these. So here's one I'd like for you to try. Okay, we'll do it together. It's I3 minus. I3 minus. All right, so iodine is happy at 7. Okay, but we have 3 of those. All right, so 3 times 7 is going to be 21. Okay, that minus sign means we've gained 1 electron. Okay, we've gained 1 electron. So our goal is to get 22 valence electrons around I3 minus. Okay, 22 valence electrons. All right, so I'm going to make I my center atom. Okay, so I will be our center atom. And then attached to that will be another I, and then attached to that will be another I. Okay. And so let's count. We need to get 22 here. So 1, 2, 3, 4. All right, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to put 17, 18, 19, 20, 21, 22. Okay, so I'm going to put the remaining 3 lone pairs. Remaining 3 lone pairs on the center iodine atom. You may wonder, why will I do that? Okay, why is this the best structure? Okay, any type of double bonds with halogens is kind of no-no. There are some cases where you'll need them, but not in this situation. The reason why I put the 3 lone pairs here is because this is how you'll get the formal charge and the octet rule really satisfied. You try putting double bonds here and the formal charge is everything. It'll be really weird and wacky. So let me explain that to you, or expand that for you. So let's calculate the formal charge of the center iodine. Okay, formal charge of this center iodine. So everyone count with me. So 1, 2, 3, 4, 5, 6, 7, 8. What is iodine happy at? 7. What's 7 minus 8? Minus 1. And there you have it. There's that minus 1 that was in the problem. Okay? So that has been accounted for. That has been accounted for. Because remember, the problem has a minus sign, so there's your minus sign. All right, octet rule for this iodine. All right, count with me. You count everything individually as 1. So 1, 2, 3, 4, 5, 6, 7, 8, that bond. 9, 10, that bond. Okay, so the octet rule is 10, but that's okay. Okay, that's okay. That's totally okay because we can call that an expanded octet. Okay, so the center atom can have an expanded octet. It's perfectly fine. You see, even though I have an expanded octet, I got my minus formal charge accounted for. Okay. All right, let's do the formal charge in blue for this iodine here. Okay, realizing it's the same as that, so I'm only going to do it once. Okay, so ready? Formal charge on this guy. 1, 2, 3, 4, 5, 6, 7. What is iodine happy at? 7. What's 7 minus 7? 0. Okay, perfect. That one and that one are the same. Let's do the octet rule for this iodine, left or right, it's the same. You count everything individually for the octet. 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. So this satisfies the octet rule. Same thing with that. All right. Next thing on the list here is looking at our center atom. Looking at our center atom. We have here 1 bond, single, 1 bond, single, so that's 2. 2 bonds, and 1 lone pair, 2 lone pairs, 3 lone pairs. 2 bonds, 3 lone pairs. Everyone see that? 2 bonds, 3 lone pairs. So get table 10. Get table 10.2 out. Let's see if I have table 10.2 here. Okay, so here we're going to get table 10.2. Let me see if I have it. All right, so table 10.2 is the situation where you have lone pairs, right? And here we've got actually 3 lone pairs. So 3 bonds, 2 lone pairs. 2 bonds, 2 bonds, 3 lone pairs. This is linear. Okay, the molecule geometry is linear. So make sure you bring this to the exam, okay, or have something open when you take your Canvas exam. So the molecular geometry of this is linear. Okay, that's what this looks like in 3 dimensions. All right, how will we get to, what's 2 plus 3? 5. How will we get to 5? All right, in terms of hybridization. Okay, how will we get to 5? Okay, we'll take 1 from S. We can take 3 from P. Okay, so 3 plus 1 is 4. I need 1 more. I need one more subshell. That's what it's called. And I'll take it from D. Okay, so sp3d. 1, 2, 3, 4, 5. That's how I will get my 5 bonds. 2 of them are single, and then 3 of them are lone pairs. So this is an sp3d hybridized iodine. sp3d hybridized iodine. Let's see if we can make this here. So we have 5. 1, 2, 3, 4, 5. So let me find something that has 5 here. here's my center iodine. Here's iodine 1, iodine 2, the center one, and then finally iodine 3. So these lone pairs, so here's a lone pair coming towards you guys. Let me rotate it. Here's a lone pair going there. See it? Lone pair going there. Aiming right at you, Josh. There's a lone pair going here. Aiming right at you, Adrienne. And there's a lone pair here coming towards me. So those 3 lone pairs are really making this linear. Okay, really distorting the shape of the molecule. So once again, lone pair number 1 going that way, diagonally. Lone pair number 2, diagonally, going towards you, Xiang. And then lone pair 3, coming towards me. So how will we draw this in 3 dimensions? Okay, so here's one way. Okay, remember, there's more than one way to draw this in 3 dimensions. So I'll have an eye. Here's this center eye in red. And then I'll have one more eye. Okay, this one, this lone pair of electron that's going towards me, we will just we'll just have it go like this, okay? This is going towards me. Okay, this is called a dash, meaning it's coming out of the board, okay? And then this one, this lone pair going towards you guys, I'll have it go like this. Again, there's more than one way to depict this, but it's going at an angle, and that's where a lone pair is. Here's another lone pair. And that lone pair towards you, Xiang. Okay, I'll have it go away from me. And that molecule is a straight line. So the molecular geometry is linear, and then this is called a dash. It means it's coming out of the board. And these that are going away from you or away from me is called a dash. Okay, so this is called wedge, and this is called dash. Okay, the dash bond and the wedge bond. The next thing is this polar or nonpolar? All right, so this iodine is pulling this way at the top. This iodine at the bottom is pulling equal and opposite. Okay, so they cancel each other out. This pair of electrons is pulling this way. Okay, that pair of electrons is pulling diagonally, so I'll put that in purple. It's pulling diagonally. And this pair of electrons is pulling this way. Okay, so if we add the vector 1 with the vector 2, okay, the net 1 plus 2 is going to be this one, this way. So something going that way pointing and going that way pointing, they all add up to one another. If you add the 2 vectors, it will go like this. Okay? Adding vectors is something you will see in physics. But so this pull this way and that pull that way, they sort of contribute little by little by little by little to each other. So the net, when you add the two, is one going this way, which cancels out the one that's pulling to the left, or the one that's pulling to the right. Okay? So is this polar or nonpolar? The answer is that this is a nonpolar molecule. Okay. Again, because of this diagonal pull and that diagonal pull, add them together, the net is something that's straight to the left, canceling out this lone pair of electrons that's straight to the right. This top iodine pull is canceled out by the bottom iodine pull. This is a nonpolar molecule. So I3 minus, sp3 dehybridized iodine, nonpolar. 2 bonds, 3 lone pairs. The molecular geometry is linear. The molecular geometry is linear. How about another example? How about we do the example that is ICl3. Okay, this molecule is called iodine trichloride. So I is happy at 7. Okay, what is Cl happy at? 7 as well. Okay, they're both in group 7 of the periodic table. But you see we have 3 of these, right? So 3 chlorines, 3 times 7 is 21. So I need to get 28 valence electrons around the ICl3 molecule. But I'm going to make iodine my center atom, because I don't know which one of the 3 chlorines is center. So let's make iodine our center atom. Right, so let's attach it to our chlorines. 1 chlorine, 2 chlorine, and then 3 chlorine. Okay. All right, counting, we need to get 28 now. 1, 2, 3, 4. All right, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Where will I put 25, 26, 27, 28? On the iodine, okay? 25, 26, 27, 28. Okay, let's put them back on the center atom. Halogens, again, for the most part, you're going to have exceptions to the rule, but halogens, especially these outer halogens, usually don't like double bonds. If you put a double bond by a halogen, it's going to really change the structure, a formal charge. It will change the formal charge. So putting these 2 valence electrons back on the iodine, let me tell you why that's a good thing. Okay, let's calculate the formal charge. That's why it's a good thing, putting them back on. All right, formal charge of this iodine. Ready? Count with me. 1, 2, 3, 4, 5, 6, 7. What is iodine happy at? 7. 7 minus 7 is 0. Okay. Best. You see the problem? If you are given this on the exam, ICl3, no charge. So we have no charge on the iodine. Good. Okay, let's do the octet for this iodine, or iodine. Okay, you count everything individually. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this has 10, but that's okay. Okay, that's okay because we got an expanded octet that gives us 0 formal charge. So that's okay. We can call this an expanded octet. All right, let's do formal charge and all that octet for this outer chlorine, realizing that it's the same for this and this. I'm only going to do it once. All right, formal charge for this chlorine. 1, 2, 3, 4, 5, 6, 7. What is chlorine happy at? 7, right? What's 7 minus 7? 0. And the octet rule for this chlorine, 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. For the octet, you count everything individually, 7 and 8. Yeah. So, right, same thing for this chlorine, and that chlorine. All right, what's next here? Looking at the center iodine. Looking at the center iodine. We have, okay, everyone ready? 1 bond, 2, 3. 3 bonds. They just happen to be single. We have 3 bonds, and we have 2 lone pairs. So will we use table 10-1 or 10-2? 10-1, no lone pairs. 10-2 with lone pairs. We're going to use table 10-2. All right? So table 10-2 is the situation where we do have lone pairs. Okay, so make sure you have a copy of this come exam time. So what is this? 3 bonds, 2 lone pairs. 3 bonds, 2 lone pairs. The geometry T-shaped. Okay, T-shaped. Interesting. So the molecular geometry, the shape of this molecule is called T-shaped. Okay, T-shaped. So that's 3 bonds, 2 lone pairs. How will we get to 5? Okay, we're going to take 1 from S, 3 from P. Okay, that gives us 4. And then how many do we need? We'll take 1 from D. Okay, we'll take 1 from D. So this is an sp3 hybridized iodine, just the same as this one. Here we had, to get to 5, we need 2 bonds, 3 lone pairs. Here to get to 5, we'll have, it's the same thing. No, 3 bonds, 2 lone pairs, 2 bonds, 3 lone pairs, 3 bonds, 2 lone pairs, kind of flipped. All right, sp3d hybridized iodine. All right, so let's do this here. ICl3. So here's my iodine. So 1, 2, 3, 4, 5. So this one has 5. So this will be ICl3. So 2 lone pairs. 1 lone pair is coming towards you guys. The other lone pair is coming in the back of me. Okay? So T-shaped. It's also coming at an angle. You see how it's coming at an angle? This one here is coming at an angle. Okay. So let's see if we can draw this in 3 dimensions, recognizing that this Cl, that Cl, and this Cl, and this iodine are all on the same plane. Okay, the same plane of my chest. So we have this iodine here. We have a Cl, Cl, and a Cl down. This pair of electrons that's coming at an angle towards you guys, I will have this, how should we do that here? It's coming at an angle. You will just do it like this. And this lone pair that's coming towards me, see right here? Lone pair coming towards me, it's coming at an angle, so I'll have it come at an angle like this. Again, there's more than one way to draw this, right? So this bond once again is called wedge. Wedge, and this bond is once again called a dash. Dash means it's coming away from you. Wedge means it's coming towards you. So this is where one lone pair is. Okay. Just put it in its little lobe. Now the question is this polar or nonpolar? All right, so this Cl here is pulling this way, okay, making it partial negative. Cl is electronegative. Okay, the Cl here is doing the exact same thing, pulling this way. This Cl is pulling down. Okay, this Cl is pulling down. This one here, I'll do it in red. This pair of electrons is pulling at an angle this way. Okay, this pair of electrons is pulling at an angle that way, diagonally. Okay, we'll call this pull 1 at an angle there. Okay, this one we'll call pull 2 at an angle there. When we add them up, they each add up to each other little bit by little by little by little, so that the net is this way. That is the net of 1 and 2. The net of 1 and 2, it's about adding vectors, so it's a little bit of a different math. So the net of this at that angle with the net of this at that angle is, adding them up, is straight up, which cancels the pull straight down in purple. So hopefully we'll see that this is not a polar molecule, but nonpolar. Okay, so this is a nonpolar molecule. Okay, because 1 and 2, that contribution at an angle adds up to straight up, cancels out by straight down. The left pull chlorine cancels out the right pull chlorine. This is a nonpolar molecule. Okay. So iodine trichloride is T-shaped. That's what the structure looks like in 3D space. It is an sp3 dehybridized iodine with 3 bonds and 2 lone pairs, and it's a non-polar molecule. Let me switch gears a little bit. Next week we will wrap things up with more practice Lewis structures. Let me tell you about something else here. I want to talk about sigma bonds and pi bonds. And then we will, again, next week, more practice, more review. Another name for a single bond is a sigma bond, okay? And that's the Greek letter for sigma. So I want you to know sigma bond and single bond are the same thing. So if I say single bond, you can automatically register sigma. And a sigma bond is an overlap of s orbitals, okay? So the s orbital looks like a sphere. Here's an s orbital, convenient. Okay, it's a sphere. Okay, the probability of finding an electron cloud or electron density is the shape of a sphere. Okay, remember an s orbital looks like a sphere. Okay, we also have what's called a pi bond. Okay. And that is basically your double bond. Okay. And that is an overlap of a p orbital. Okay, so there's p orbital has 3 subshells. It has a dumbbell that's shaped along the x-axis. okay, that's called a node, where there's zero energy, zero wavelength, is a dumbbell along the x-axis, y-axis, and then the z-axis towards us and away from us. So that is an overlap of one p orbital, I should say. Okay, one. So either this one along the x, either that one along the y, or that one along the z. Successful overlap, that would be a double bond. Okay. There's also a triple bond. Okay, that is an overlap of not one p orbital, but two p orbitals, excuse me. Of two p orbitals coming together. So while a double bond is one p orbital overlap between two atoms, a triple bond is two p orbitals overlap coming together. Let me give you some examples. Okay. The example I'd like to show you is a molecule known as formaldehyde. Okay, so for the biology people, okay, or for the people that like working in labs, anatomy labs, and all that stuff, formaldehyde is a good fixative. So let me quickly draw the structure for you. Okay, so carbon loves 4, so I'll put one H here, I'll put another H here, and I'll put a double bond, oxygen. All right. Carbon loves 4. Okay, that's, if anything you get from this class, realize carbon loves 4. Okay, 1, 2, 3, 4. All right. So I want you guys to pay special attention to this double bond here. Okay. So I'm going to just rotate this molecule. I'll rotate it 90 degrees. Okay. So remember a single bond. A single bond is also known as sigma. So anytime I say single bond, you can also say sigma. And that's an overlap of an s orbital, which looks like the shape of a sphere. Okay, so it has to be a constructive overlap. Remember, these things are waves. Okay, so here's an s orbital of H. Here's an s orbital of this other H, hydrogen. Here's the s orbital of carbon. They're kind of overlapping. Okay. They're overlapping, they're aligning, there's good vibes between them. Okay, so we call this constructive overlap. Okay. So in pencil, I'll have the overlap of an s orbital. Same thing with the s orbital of carbon with the s orbital of oxygen. Okay. That sphere, or that circle, 3-dimension is sphere. These waves are sort of lining up with each other. Okay, so there's good overlap of the s orbitals. But remember, again, let's focus our attention on the double bond. The single bond is an overlap of an s orbital, but the other bond that makes it double is an overlap of a p orbital. So the overlap of a p orbital, I'll just, one of the p's. Okay, one of the p's, either x, y, or z. So here's how that would look like. Here's a p orbital of this carbon, and it's overlapping very nicely with the p orbital of this oxygen. Okay, so there's very nice overlap. Trying to draw this in 3D, but so here's a p lobe from the carbon, And they're overlapping constructively, because when two waves combine, they can combine constructively or destructively. These p orbitals, which are also waves, are combining in each other so that there's good overlap to make this double bond. So a double bond is one p orbital, p overlap in red, and then s overlap in pencil, which is a sphere. Okay. So that would be a good example of formaldehyde. Let me just amend this here. So let me just say a double bond is an overlap of one p orbital and an s orbital. Okay, so and a triple bond is an overlap of two p orbitals coming together as well as an s orbital. Okay. Which again is a sphere. Okay, the shape of an s orbital is a sphere. All right, so here's an example of a double bond. Let me give you an example of something with a triple bond. Okay. A piece of paper. Example of a triple bond would be cyanic acid. Cyanic acid. By the way, let's go back here to this formaldehyde. What's the hybridization of this carbon? Okay, let me rephrase that. Okay, so look at this center carbon. One bond. Second bond is a double bond. And then a third bond is a single bond. So we have 3 bonds and 0 lone pairs. So what's 3 bonds and 0 lone pairs? Okay. We will use, not this, but we will use table 10.1. Okay. Table 10.1, 3 bonds, 0 lone pairs. You'll see that it's trigonal planar. So the molecular geometry here is trigonal planar. And to get from 3 to 3 and 0, 3 plus 0 is 3, it's going to be S is 1, and then we're going to take 2 from P. So this is an sp2 hybridized carbon. Right, remember, hopefully this will all ring a bell. And is this polar or non-polar? This is 100% polar. That oxygen is going to pull like mad. And within formaldehyde, you have a region that's partial negative, and then you'll have a region that's partial positive. So formaldehyde, okay, has a pi bond, which is a double bond, but also it's an sp2 hybridized carbon. It's polar, and 3 bonds, 0 lone pairs. Okay, formaldehyde polar, sp2 hybridized carbon. 2 plus 1 is 3. 3 bonds, 0 lone pairs. Here you see the nice overlay of the P lobes. All right, let's go to our next example, cyanic acid. Okay, this is HCN. All right. So hydrogen is happy at 1, carbon is happy at 4, nitrogen is happy at 5. So we need to get 10 valence electrons around cyanic acid. All right, let's make carbon, which absolutely, positively, without a shadow of a doubt, it loves 4. Okay, so let's make carbon our center atom. How will we get 4? Well, hydrogen is very, very small, okay? So we will put hydrogen as a single bond. Then how will we get to 4? 1, 2, we'll do a 3, we'll do a 4, and that's where we'll have our nitrogen. Okay, C triple bond end. Looking at this carbon here, 1, 2, 3, 4. By the way, 1, 2, 3, 4, 5, 6, 7, 8. Where will 9 and 10 go? Not on the hydrogen. Can't go on the carbon. Carbon is set at 4. It will go on the nitrogen. So that would be a good Lewis structure for cyanic acid. Carbon here. Let's look at the formal charge. Ready? 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4? 0. Octet for this carbon. Okay, so ready? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the octet for this carbon is satisfied. Okay, let's look at this hydrogen here. Okay, 1. What is hydrogen happy at? 1. What's 1 minus 1? 0. And then the octet for this hydrogen is going to be 2. Okay, 1, 2. That's fine. The octet rule has a lot of variations. All right, let's look at the formal charge of this nitrogen. Formal charge, ready? 1, 2, 3, 4, 5. What is nitrogen happy at? 5. 5 minus 5 is 0. All right. Octet rule for this nitrogen. Count everything individually. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's the octet rule. All right, we have 2 bonds and 0 lone pairs. 2 bonds, 0 lone pairs. One bond is single, the other bond is triple. 2 bonds, 0 lone pairs. So table 10.1, 2 bonds, 0 lone pairs. The molecular geometry is 2 bonds, 0 lone pairs. The molecular geometry is linear. Okay, the molecule is a straight line. Okay, 2 bonds, 0 lone pairs. Shall I bore you with this? 2 bonds, 0 lone pairs. One happens to be double. One happens to be triple. The other happens to be single. It's 2 bonds, 0 lone pairs. No lone pairs, very nice, sweet bond angle of 180 degrees. Right, SP is the hybridization. To get to 2 bonds, 0 lone pairs, we're going to take one from S and then the other from P. It's a hybridized carbon. And then finally, this is a polar molecule. That nitrogen is pulling. Okay. So we have a partial negative end and a partial positive end. This is a polar molecule. All right, cyanic acid, SP hybridized carbon, 2 bonds, 0 lone pairs. Molecular geometry is linear. It's a polar molecule. So the last 5 minutes or so of class, I want you guys to focus on this triple bond here. All right. So let me draw this again. Okay, so we have H, C, N. All right. So as we stated before, single bond is the same thing as sigma. So I'll draw the single bond overlap between the s orbitals. Okay, so here they are really overlapping nicely. Same thing on this end. Okay, so we got some nice overlap here along the s orbital. Good overlap with S. Okay, that's sigma. All right, so that's one of the bonds. So we have the triple bond here. That's going to be an overlap of 2 p orbitals. So I'm going to draw one of the p orbitals like we've drawn before. Okay, so I'll do it in red. Okay, so here's what the P lobe looks like. It looks like a dumbbell, right? Okay, so here we have some nice, good overlap. So we got some good overlap here. For those of you that like sketching, you may like this part of the course. All right, so that's one P lobe overlap. But remember what I told you a triple bond is. Okay, it's an overlap of an S. We got our S. It's an overlap of not one P but two P's. So I'm gonna draw a second P lobe. I'll do it in this lime green. Actually, I'll do it in... maybe I'll do it in this. Okay, it's going to be perpendicular. Okay, so remember, these p orbitals are perpendicular to one another. So that would be in the purple. And that is how we construct a triple bond. Okay? We have some nice overlap between p orbital 1. So I'll call this p lobe 1 in the purple, and then in the red we'll call p lobe 2. Okay? The overlap of the p orbitals in red of carbon, the overlaps of the p orbitals of carbon with nitrogen, and an overlap of a second p orbital of carbon with the second p orbital of the nitrogen. The bottom line is that a triple bond is an overlap of two p's and one s. All right, have a good weekend. Hopefully I'll have, I do plan to have the study guide available, and next week we'll just review and do some wrap-up stuff. Okay? Just some wrap-up stuff and review. Monday, Wednesday, Friday we'll meet. Monday, Wednesday, Friday we'll meet. Come with your questions or doubts. And thank you guys for coming. Appreciate it.